All right, we have discussed the idea of work and energy and just this last video, potential energy, and we're now ready to bring in this concept of conservation of energy, this extremely powerful tool that we can use to solve problems. And so before we get into the conservation of energy, we need to make sure that we're all on board with this idea of a system. A system is the object or the objects that you've identified for which we're tracking or cataloging the forms of energy or the total energy in a given problem. And so your system can be as small as one particle or one object or one atom, and it can be as large as, the entire universe. And so defining your system is going to be important because that's going to determine what energy terms show up when we start to think about the total energy of our system. So forms of energy that we're going to see, well, two that we've already talked about: kinetic energy, so the energy associated with the motion of the objects in your system, and then potential energy. So we've talked about conservative forces. Those forces have associated potential energies that we can catalog. And so gravitational potential energy and spring potential energy are two forms that we'll see in 101. If you add up the kinetic and the potential energy, we refer to that as the mechanical energy of the system. And I've got written over here this E. E equals K plus U, so that's our mechanical energy of the system. Other forms of energy that may show up when we're starting to track or catalog energy is work done by non-conservative forces on our system or on the objects in our system. So the idea behind the conservation of energy is that the total mechanical energy, the kinetic plus the potential, that total amount of energy at any two times, states A and states B, that total amount of energy remains unchanged unless there is work done by non-conservative forces during that transition from state A to state B. And so writing this out in equation form, the work done by non-conservative forces is equal to the change in the mechanical energy from point A to point B. Now remember, when we're looking at the change, we're really looking at the final energy minus the initial energy. And so any form here, pick any of those two equal signs and you can string them together. So the conservation of energy here is going to show up in a bunch of different ways. Specifically, when our system is isolated, that is, there are no non-conservative forces acting on our system between points A and B, we call that system isolated. That means that work done by the non-conservative forces is zero, and the total change in the energy, the change in the mechanical energy from A to B, is equal to zero, right? And this is what we mean when we say that the total energy of the system is conserved, no matter what forms the energy is in, whether it's potential energy, kinetic energy, doesn't matter the forms. If you add up all the energy, you always get the same result. Now, when do you not get the same amount of energy? Well, that's when you've got work being done, forces from outside the system interacting with your objects, and so work can be added or removed from your system in those cases, much like we talked about your bank account and the idea of changing the amount of money that's in your bank account. The total amount of money, whether it's in dollar bills or coins, remains constant until you add money to your bank account or remove it. And this is the same idea as the conservation of energy. Our most common non-conservative force that we're going to see is friction, whether it's on a surface or air resistance with an object moving through a fluid. So let's just look at an example here to see how we leverage the conservation of energy to solve a problem really quickly. So I've got a block moving to the left at 10 meters per second. There's no friction in this problem, and the block is going to slide up this ramp, and of course it's going to come to rest at some point because, as for energy arguments, as the block travels up the ramp, the gravitational potential energy will increase, the kinetic energy will decrease, and at some point the kinetic energy will decrease to zero, and that'll correspond to our highest point that we can reach. So we want to find this height h that the block reaches, and so the general approach for conservation of energy problems is to pick an A and a B, or an initial and a final, a state A, state B, that you want to catalog all the types of energy that are present in your system, and then add all of that up. So I've picked state A down here when the block is moving at 10 meters per second. And then my state B is up here at the top when the block is no longer moving, when it's reached its maximum height. And again, no friction in this problem. So let's catalog all of the energy at state A. Well, the mechanical energy is just the kinetic plus the potential. So kinetic energy, 1/2 mv squared, and potential energy, mgya. Now, we mentioned this in the videos, we've talked about it in class. The potential energy is position dependent, and so the potential energy at any given location is arbitrary. So I'm going to choose this location as y equals 0, which means my initial potential energy due to gravity is going to be 0. And so initially all I have is kinetic energy, and instead of plugging in numbers here, I'm just going to leave it as 1/2 mva squared. Okay, so that's it. I had two potential energy terms. One of them is 0, and so I just end up with kinetic energy at the start. Well, what about at B? So let's write out the total energy at B. Again, kinetic plus potential. Kinetic energy, 1/2 mv squared. Potential energy, mgy. Notice here I don't have any spring potential energy because there's no spring in the problem. Now, state B is when my block reaches its maximum height. By definition, that's going to be when the speed is 0. So this term is 0. And all I have for the total energy at B is mg, and then the height here is h. The y position is h. And so this is my total energy in state B. Now, conservation of energy tells me that the work done by non-conservative forces, which in this case there are none, is equal to 0. That's got to be equal to the change in the total energy of my system. Well, my total energy in state B is mgh. My total energy state A is 1/2 mva squared. And again, that's got to be equal to 0. That tells me that mgh, so the final potential energy due to gravity, has to equal the initial kinetic energy in my problem here. Now you'll notice the masses cancel out. And if I solve for h, I get that h is the speed squared divided by 2g. So the initial speed squared divided by 2g. When I plug in the numbers there, my initial speed was 10 meters per second. I get 5.1 meters for the height that the block reaches when it was launched with this initial speed of 10 meters per second. Now, notice in my analysis, all I did was take into account the initial speed, right, 1/2 mv squared, and then the final location that this object comes to rest. Since there's no friction, it doesn't actually matter how my block gets from the ground to its highest point, since the only forces that are acting on my object during this process that's influencing the motion is the force due to gravity. The maximum height is going to be 5.1 meters regardless of if I launched this block 10 meters per second in this direction and it goes up the ramp, or if I launched it straight up at 10 meters per second. In both of those cases, the block will reach the same maximum height of 5.1 meter. Now, of course, if there's friction on this ramp, now all of a sudden it is going to matter the path that the block takes, and if the block is going this way, it will reach a lower height, maximum height, than without friction, right? And that's because if there is friction, then there's a non-conservative force doing work, and that is going to lower the total mechanical energy of the system, right? that work done by friction is going to remove energy from the system. That's energy that can't be recouped. In this case, though, the block slides up and reaches the maximum height. With no friction, when it slides back down and reaches this point, it's going to be moving at 10 meters per second. Right? So on the way up, the kinetic energy is getting converted to potential, gravitational potential, and then on the way back down, the gravitational potential energy gets converted back to kinetic. And this is the approach for how we set up and solve problems using the conservation of energy. If you have more objects in your system, then you just have more terms here that you add up.